Welcome back, everybody, to the Additive Snack podcast. I'm your host, Fabian Alefeld, and today we have a fantastic, maybe even famous guest joining us, and that is, of course, Alex Kingsbury. Alex Kingsbury leads the additive manufacturing business at nLIGHT, but has been deeply involved in various facets of the additive manufacturing industry for years. And therefore, we'll dive into a few parts of that today. We'll, of course, talk about the groundbreaking advancements of laser technology and specifically of the technology called beam shaping, which at the moment is making a lot of noise in additive manufacturing. And we'll dive deeper into that. But we'll also, of course, then therefore talk about the material properties and productivity implications that it has. But also the implications on different industries and applications. But we'll also dive a bit deeper into Alex's background, how she got into additive manufacturing, and the various other insights that she can share with us today. So therefore, without any further ado, Alex, welcome to Additive Snack.
Thank you, Fabian, for having me. I'm very honored to be here. I'm a fan of your podcast, so it's a great honor to be a guest. Thanks for having me.
Well, I'm a fan of Alex Kingsbury. I'm also a fan of the various publications that you are a part of, and where you also, of course, started printing money. And I am a fan of that podcast. So thank you for enlightening us back then, and also now as a guest on that podcast from time to time. And before we go into nLIGHT and lasers and beam shaping and all these interesting innovations, let's talk a bit about you. You've had a very interesting journey throughout the additive manufacturing landscape and industry. You've made moves for the additive manufacturing industry. So take us a little bit back in time. How did you get into the technology?
Well, I guess I started. I did chemical engineering as my undergraduate, right? So I started my career as a process engineer, and I was working in the mining and oil and gas industries for a period of time as a graduate. And part of my work in those industries was doing something we call cost engineering or cost modeling, right? So this is really where you are able to take some engineering expertise and work up an engineering model, but then combine that with a cost model. And this is a really helpful skill in what's called pre-feasibility studies in the mining and oil and gas industries. And anyway, this is a very long way of saying that I somehow found myself at CSIRO. That stands for the Commonwealth Scientific and Industrial Research Organization. So if you're familiar with the national labs in the US or say a Fraunhofer in Germany, it's a similar sort of concept where you've got basically industrial research happening that is a public-private partnership to some extent. And one of the things that they were doing at CSIRO and a skill that they really needed was my exact skill. So I got very lucky in that way, and I was looking to move into an environment that I would be really challenged. Because I liked the work I was doing, but I really wanted to be more at the forefront of new things and innovation. And so I started working at CSIRO. Like I said, they needed my skill set in particular, but they really needed it for a lot of the very early stage research that they were doing. So the idea there was to develop up a commercial model around the new research that was happening at CSIRO to determine if there was a good market fit for that research, that end product of that research. And then to go and do the work to find the suitable partners for co-investment, to find some funding sources. A lot of the work that we were doing was all in titanium. It was about creating value from the natural resources that Australia has in producing metal powders. And so we had a number of different processes making metal powders, but that led us further downstream into manufacturing and powder metallurgy and powder consolidation techniques. Now, I think this is all probably starting to come together, hopefully, because it was around 2011 that I joined. Metal additive manufacturing was becoming a much more serious concern right? A
Cool.
much more serious technology. And we saw that there was an opportunity for our powders that we were making to be used in additive manufacturing. So we added it to that list of downstream manufacturing technologies we were working on. And then it just really took off from there. And luckily I got to take off with it. So we had, a metal printer, and that was really successful. That was an Arcam, actually, an e-beam machine.
Ah, cool.
Um, my first printer. A lot of people joke that that's a pretty tough, hard starting hurdle to get over. Um, but that grew, and then the idea or the mission sort of changed a little bit, actually, because it was around trying to cultivate an industry in Australia that at that time didn't exist. So we then brought in a whole lot of different modalities of printers. A laser powder bed was the next modality that we brought in. We brought in D&D, we brought in binder jet. We were already doing a lot of work in cold spray, which you know then and earlier had been used as a coating technology. We were doing work to transform that into an additive technology. And so it was a great opportunity. And that's essentially how I got started. I've been through a couple of different side journeys from there, and now here I am.
Yeah, super interesting. And before we go into nLIGHT, how would you compare the Australian additive ecosystem and adoption to some other markets like the US where you're at now?
Yeah. Um, it's a good question. It's one where we had a lot of early successes, and actually, a big part of that push for industry adoption that we were doing in those early phases, and I'm sort of talking around 2015-ish, 2014, 2015. Um, and we had a lot of good success in medical. So we have a really strong medical profession here in Australia, and we have a very strong pedigree of not only medical professionals but also the research infrastructure that supports them in Australia. It's one of our real competitive strengths, and so we were able to do some really fantastic early projects at CSIRO in collaboration with local industries and local surgeons, doing some world first. Which, Fabian, you've been around for a while. I'm sure the world firsts were a real thing that were happening. I think we've sort of thankfully moved on a little bit as an industry from that. But the world first back then were pretty exciting.
Yep.
And they were, we did a 3D printed heel. So that was a man that had cancer in his calcaneus bone, is what it's called. The typical treatment for that is to amputate below the knee. And in this case, we were able to work with a local company, Anatomics, and they were able to design this heel implant. We printed it. We worked with the surgeon, and then that was a successful outcome for that patient. The guy kept his leg, and he was up and walking. And then another one, which was a tumor on a rib cage. So the rib cage needed to be largely replaced, and we worked on doing a rib cage implant, also a world first. So um, this is a long way
Interesting.
of saying that the medical profession really was an early adopter of additive in
Mhm.
those early days in Australia in particular. But as I've already alluded to, we have a strong mining and oil and gas industry in Australia, and so those industries too have followed suit to some extent. We have some great, again, research infrastructure in Australia, and a really, really strong educational uh, basis, I guess, across the population.
Mhm.
And so that's been something that's really enabled additive manufacturing to flourish in Australia.
Super interesting. Yeah. I think Australia isn't really on the map of many people when they think about additive manufacturing, right? But it sounds like there's way more research and adoption going on than the public eye may see. At least that I experience.
And there's a
Um,
couple of like sleeper Australian companies that you don't realize they're actually Australian until you kind of start looking under the hood a little bit more. But,
yeah.
they've all done a really good job of integrating themselves into some of those really big end user markets, like for example, in Europe and in the States.
Yeah. Yeah. I mean, I know Conflux, for example, is one of those players that,
Exactly.
have a lot of IP around thermal management. I think Doc Cells is a really cool company, right? A podiatrist that's really has a product that's I think is quite unique um, in the orthotic space because it really brings the professional podiatrists together with manufacturing community. So yeah, I agree. There's a lot of cool stuff happening there. Now I remember then last year or so there was a picture of you in front of the U.S. Embassy. Uh, Stay tuned, something cool is about to happen, and it moved across the pond. And you started nLIGHT. So what was that transition from, more research focused and probably even more application focused in some ways to a laser company that is doing very interesting stuff and is transitioning, I'm guessing, from conventional and other manufacturing technologies now into additive manufacturing, where you lead that business.
Yeah.
What was that like? What made you make that move and decision?
Yeah. So I've always been on this bridge between research and industry, right? If I'm in a research environment, I mean the last position I held before coming to nLIGHT was as an industry fellow at RMIT University, right? So I was that kind of the industry person in a research environment, and then usually vice versa, so more of a researchy person in an industry environment. One of the really cool things about my role at nLIGHT is I get to have a very commercially oriented role, which I'm really, really relishing, definitely relishing that opportunity. As much as there's some cool stuff happening in Australia, opportunities of the scale that, of the role that I'm in now really don't exist in Australia. And so coming to the States it's a big move. You yourself have done an international move, and you know what
Yeah.
what's involved. But I saw the opportunity to really contribute in a meaningful way, to keep learning as well, because I think that's always been what characterized my experience is that I love being in roles where I can keep learning. And I saw an opportunity to work with some really, really impressive people too. And and I think there was really two big things driving my decision to move to nLIGHT, which was number one was the people, as I said before. I can tell you how I even came past this job in the first place. That's a sort of a funny story, but the people are unreal. And then number two, the technology that nLIGHT has, which I believe and it certainly had a strong conviction of the fact that this was going to be very game changing for additive manufacturing. And I saw the opportunity for this technology in our market, and I just wanted to be part of making that happen. And so, hence, here I am in Southwest Washington,
Yeah.
in the Pacific Northwest. Yep, I've been here for nearly a year. And I tell you what, like I said, I always just want to keep learning new things, and my learning curve has been unbelievable. Not only in terms of just knowing more about lasers. I mean, there is just so much to learn about lasers. As additive people, we like kind of tend to take it for granted that we have power coming out, and it just is there and it's stable and we don't question it. There's so much involved in making a laser. Um, and then also on the commercial side, I mean, the team that I get to interface with, the exec team, or like an extremely experienced exec team, and very stable too. We've got people that have been there for 10, 20 years. And so being around those people is just an exceptional opportunity for me.
That's awesome. Yeah, I know it's a big move, but it makes it easier if you have that passion and purpose for the technology and the company.
Absolutely, absolutely. Yeah,
Yeah.
yeah. I think it's essential. You need to be 110% convinced that this is a good idea. And then you need to remain convinced once you've moved.
Yeah. A new spot is once you get over the honeymoon phase, you need that in order to go through the bump. But you mentioned learning, and I am curious to learn more about nLIGHT and the technology. I even took some laser classes in college, but if you
You've
don't
done
use it
more than
really,
me.
so yeah, I've forgotten a lot. So take us a little bit on a high level. How is nLIGHT's laser technology different to what we're using mainly today in the additive manufacturing industry?
Yeah. So one of the things about, maybe a good place to start is how is nLIGHT different from most other laser manufacturers? Which is that, for starters, we're a US based laser manufacturer, which is quite unique. We're fully vertically integrated, right? So we make everything from the chip in the semiconductor laser right through to the fiber, and then even to, multi-laser systems deliveries, right? So subsystem, laser subsystems. And it's highly, highly unusual to have that level of vertical integration in laser manufacturing.
Hmm.
But what that means is that when you have expertise within the company across the whole vertical chain, um, the ideas are just flourishing, right? And there are so many different ideas around how to improve laser technology, particularly to make it specific for the application, right?
Hmm.
Lasers in outside of nLIGHT are very much a sort of a commodity product. And the same laser used for additive is the same laser used for welding, for example. Whereas that's not sort of the philosophy at nLIGHT. We like to really think about the application and make the laser to suit, right?
Okay.
And we have that level of control because we have that full vertical integration, right? And so it's really this positive breeding space for innovation to happen in laser design and delivery. The other thing about nLIGHT too is that we are a dual use technology company, right? And what that means is that about half of our business is in defense, laser applications in defense, and the other half of our business is in commercial.
Hmm.
Um, and there's a lot of really good examples, particularly in the States, of how that is a really beneficial way to run a technology company, because you get a lot of that, um, uh, those really big sort of, moonshot, uh, innovation technology, development ideas that come through from defense. But then
Hmm.
all of that knowledge and know-how at a fundamental level passes through to the commercial side. And so we see improvements in commercial technology because of the investment in defense. So we're able to do that in nLIGHT really, really well.
Interesting. Yeah. I mean, you see those trickle down effects from highly innovative, high cost, high value applications in defense, or even in other government sectors that then over time find their way into more commercialized and also more affordable products.
Yeah.
Now, when we talk about beam shaping, we talk about Gaussian laser profiles versus donut shape profiles. Um, can you maybe a little bit first about how nLIGHT identified additive as a market to go after? Because right, nLIGHT is not an additive company; it's a laser company that happened to
Yeah.
identify additive as a potential. And how do some of these innovative technologies that nLIGHT has developed find their way into additive? Additive find nLIGHT, that nLIGHT find additive, and how are you now integrating into this new sector for?
So I'll do my best to answer this question, given that I was not around at the beginning of additive in nLIGHT, of course. But as I mentioned, you've got this access to the whole vertical chain, so you can really think creatively around the possibilities. The art of the possible for lasers.
Mm-hmm.
And in that process, there's a lot of work being done around beam shape manipulation, right? So you want to try and manipulate that beam shape for all different types of reasons and all different applications. Um, we were active in cutting and welding lasers, right? So delivering to those two markets. And there's some particular beam requirements that those markets will drive and have driven. But really, and I think what we're alluding to here is that the genesis of our a product that we have called Corona. Um, funny that it's named Corona, right? Because obviously Corona means a different thing to us now than it maybe did, way back when it was invented. But the idea is really cool. And it's about being able to manipulate the beam such that you're throwing the power into a ring shape, but you can also bring it back into the center, and you can have this sort of continuous way of taking power from the center and moving it into the ring and then back again. And you've got complete control over that spatial resolution of the beam. And now Corona as a sort of a more platform technology is relevant to many different markets, not just additives. But what
Mm-hmm.
was found is that, and particularly, or you said donut and I said ring, but we're talking about the same thing, putting the power into the outside of a ring as opposed to sort of a central core. And what we found in additive is that if you're using a ring shaped beam, then you can really affect some different changes within the melt pool. First of all, the melt pool size. You can make the melt pool a lot wider than you can with a Gaussian. A Gaussian, so it just your classic sort of bell curve, right? Is what people understand it to be. So you can make the melt pool a lot wider, but you can also make it a lot more stable than you can with a Gaussian beam. And and so that is relevant for additives because, of course, you're doing thousands of different little welds to make an additive part.
Mm-hmm.
And then it does two things. Well, it does a couple of things, but first of all, you can massively increase your productivity. Now, what has additive been crying out for so long? Of course, the first printer, LPBF printer, that I bought was a single laser, 400 watt, printer, and it's low. There's been continual efforts to work out ways in which we can drive more productivity out of our machines. Um, and fundamentally, what we've been limited by is this Gaussian beam, this shape. It's not shaped ideally for a layer. A layer is flat, and the Gaussian is not. And they're also very thin, traps. And there's only a certain amount of power that you can get into your powder bed without making that melt pool unstable. So with a ring
Mm-hmm.
beam, what you can do is you can widen your spot. You can create a much more stable, flatter melt pool. And because you're making a much more stable melt pool, you can throw more power into it, which means you can also do things like increase your scan speed, increase your layer thickness. Also that stable melt pool, it just means that you've got so much more of a process window that's available to you. So using a ring beam essentially drives productivity, and that was what additive was crying out for at the time. So the AFX laser, this beam shaping laser, is what was released in 2020. For obvious reasons, we decided not to go and call it the Corona AFX. I think in 2020 would have been a extremely
Yeah.
tone deaf thing to have done. But
It could have
it's
been both ways, right? More publicity, in a way. Yeah.
um, but anyway, it is this Corona technology that is behind what we know as the AFX laser.
Okay, super interesting. I know we had Ben DeMarco on the show months ago. Back then he was still at Ohio State. Now he's at America Mix, but he did a really good comparison of painting, right? Where
Yeah.
the Gaussian laser is a pencil, where you pencil in the infill and whatever, and with the Corona or the ring shaped laser, you take the big brush or the roller and paint, which of course increases your speed and your productivity for a certain defined surface.
Yeah.
Is that still a good analogy
It's
to?
a great analogy. I love using it, and I've done plenty of house painting in my time. And so I think we can all very, very quickly understand, why would when you go to paint a house where you've got, windows and trim and architraves, you're going to use a different paintbrush to paint the trim, for example, on your window. It's extremely fine, extremely detailed. You'll have a very
Mm,
small, very fine brush that is suitable for that kind of painting. But then, of course, you're not going to take that very fine brush and then try and paint a whole wall with it. It would be not very productive use of time. And it also, I would say, lead to a less good outcome as well, right?
yeah,
A roller is just a smoother way of applying paint. So it's a fantastic analogy that works very well. And Ben does a great
perfect.
job of explaining it as well.
Yeah, no, 100%. He's probably done it many times in his time at Ohio State. Then, um, let's dive a bit deeper into those two advantages that you talked about. So, you talked about improved material properties because my melt pool is more stable and I have less energy in a small area of the powder bed. But also, of course, therefore productivity. I mean, were a cost engineer
Mhm.
a while back, right? So you know the impact of engineering towards a cost target and towards and how much that unlocks applications. So um, I guess my question is twofold. Number one, in what ways are material properties improved, and what types of in terms of 1.5x, 2x productivity gains should we expect to see from adopting nLIGHT's ring laser technology or beam shaping technology?
Yeah, sure. So, I mean, you know that soot and spatter that we get off a melt pool is one of the leading causes of defects in additive manufacturing. And the reason that we have soot and spatter, and our understanding of it too, by the way, has just really increased a lot over the last couple of years. But, essentially, if you're applying a single point of heat input, you're creating Marangoni forces within the melt pool. So it's a push down and then a pull up. Um,
Hmm.
and, and that takes molten material from the melt pool and pushes it up out there into the gaseous environment above it. And that's what we know as soot, right? And so, and that kind of soot too is very detrimental to your part quality because it's often large, slightly oxidized particles that will fly up and then sometimes can land back in an area where you're going to be melting. And so that large oxidized particle gets trapped inside the part, and that can create not only porosity around it, but also reduces fatigue resistance, for example. The other thing you do when you're applying a lot of centralized heat is your what we like to call selective laser boiling your melt pool, not melting, right? And plenty of the materials that we work with in additive are alloys. They have there's a number of different components in the alloy, and some are more volatile than others. The magnesium is a really good example of an element that is more volatile and has a boiling point that differs to, say, aluminium. And so you can vaporize that material in the alloy. And when you do that, you start to also create these effects within the melt pool that it exacerbates certain spatter. But you also create porosity as well. And that's also if you get an excessive vaporization, that's what leads to keyhole welding as well. It happens in additives.
Mm,
Anyway, so there's a couple of fundamental things happening in the melt pool, but back to the properties, which are if you're using that Gaussian beam, you're getting a lot of additional soot and spatter that will lead to a lot of porosity and fatigue reduction. and also just a less stable outcome for your built part, right? So if you've got some vaporizing material, you're then starting to, and in some cases you can go outside of the material specification for your part because you've vaporized off so much of one alloying constituent.
Hmm.
Um,
Hmm.
and then the other thing we see with beam shaping or using a ring beam to consolidate material is that there is, on every lot of mechanical properties you do, you've got these error bar. The error bar for beam shaping is always a lot smaller. And that really speaks to that melt pool stability. If you've got a much more unstable melt pool, your outcomes are just less well known and less able to be predicted, which is also something we struggle with in additive manufacturing, is this lack of repeatability, lack of
Hmm.
consistency, right? And it's very symptomatic of the processing conditions that you're using in a system. So being able to stabilize a melt pool then leads to a lot better consistency of outcome and a lot better fatigue resistance in particular. You've got a lot less certain spatter, less porosity, more reliable, more consistent, and better mechanical properties. Um, and then I think moving on, you're talking about like 2 times, 3 times. This is totally material dependent. The other thing that we find too is that, um, those different beam settings. So, in the AFX laser, we have 7 different beam settings and they vary from a super Gaussian at index 0
Hmm.
up to a maximum ring in index 6. And then you've got everything in between. Some materials respond better to different indexes, somewhere, in some sort of intermediate space between 0 and 6. And so we've got not only a geometry dependency for our beam settings, our index settings, we've also got material dependency. And then sometimes we want to do a trade-off between productivity versus quality. But being able to access all of those different indexes means that you have the freedom and flexibility to choose your processing condition. So anyway, back to the point, back to your question, which is how much productivity can you get? Classic engineer's response, it depends, of course.
Yeah.
Um,
Awesome.
but, typically what we see is that you get at least 2 times the productivity, at least two
Okay.
times. Anything up to 8 times the productivity, which is enormous. Um, and then, and of course, this can be also part dependent because if you've got a really small part with a lot of fine details, or even just a part with a lot of fine details, you're going to be getting less of that productivity advantage from beam shaping than you would if you had a really big part that just had lots of areas needed for bulk consolidation. Going back to that painting analogy, right, where you're using a finer bead for a finer detail, and you use that
Mm.
larger spot size with the ring for more coarse detail.
That is a really good point because, of course, no technology is the solution for everything. But of course, innovations like beam shaping, um, just cry for people to really dive a bit deeper into where do I apply beam shaping first? And you just kind of alluded
Mm.
to it already a little bit, bulky parts that are big with a lot of stress, maybe also with certain materials, may be better suited for companies to think about beam shaping first versus a highly regulated, fine detail, thin wall parts that's already in production. So which industries do you see as early adopters of beam shaping, and how do you approach it to also develop the business of it?
Yeah, of course. So it's interesting. We see that the productivity story is kind of like that hook that gets people in, that want make them want to talk about beam shaping and AFX and what we have. But usually it's what keeps people interested is the quality story. Um, And that is often seen as being sort of more important. Of course, if you've got a part that we've just spent, multiple days building, and then you realize you've got to scrap it because it's gone out of specification, that's more painful to you than a slow build. Um,
Hmm.
but in terms of industry, yeah, again, I've already alluded to it, right? These large bulky parts are perfect. And when I say bulky, don't think kind of, some huge bulky thing. Bulky and additive can actually
No,
be a couple of millimeters, right?
yeah, we're not printing cubes and blocks. Yeah,
Yeah,
except for
exactly,
that, I
exactly.
guess. Yeah.
But where I see it working really well, where you've got when you've got a need for productivity, but you've also got a need for quality and consistency and repeatability. And obviously that's important for all three different parts, but where it's really critical is in large area format printing, right? If you're creating larger parts, where you not only want that productivity benefit, but you want the quality benefit as well. Because a part failure partway through a build is just catastrophic to the economics of your build. And yeah, and so on that in that way, we find that there's a lot of receptivity for the technology in aerospace and defense, particularly. There's a lot of and there's also a lot of interest in industrial as well, industrial application.
Hmm. Hmm.
Beam shaping with Inconel, with stainless steel. This is like really well documented. It's just so much easier, better, superior, faster, right? Um, and so that feeds really well into those industries. Yeah. And then I think just that multi-laser, as I was talking about, we do these subsystems, laser subsystems. We've designed our laser subsystems all around a multi-laser platform. I think if we look at the industry and the trends that we're increasingly seeing more lasers applied to printers, right, today than what we were, starting with. Like I started with single laser platform, um, and then we've got this like increasing need to add more and more and more lasers. I mean, I think largely we all acknowledge that there's a lot of diminishing returns that happens there. Um, but I think multi-laser platforms in general are here to stay and are the most relevant. So being able to create a laser that's not only suitable for productivity and quality, but also provided in a package that is really optimized for multi-laser performance. And that's one thing I think as an industry we've been struggling with a little bit. Is being able to do this sort of laser performance, and that's something that nLIGHT does really well.
Okay, interesting. And yeah, I mean, I agree with you. Also, just adding more laser for productivity is definitely not the answer, especially when we look at cost and when we look at stability and uptime. More lasers also means higher risk of one of the lasers failing if you have 64 in a system. So
64 is a lot of lasers.
yeah,
And every laser needs a scanner, right?
yeah,
And they
yeah.
usually need a collimator, right? And so there's just additional equipment that goes along with every single laser. And so finding sort of some more intelligent ways to deliver deliver power to a powder bed is really what's required. But you're not going to get there unless you have I mean, maybe I'm being a bit biased here, but you're not going to get there unless you have a laser provider that really knows and understands the applications that are driving the technology and why we're creating the platforms, the way that we are. We see this in additive, right? A lot of these platforms have been sort of much more driven by application. We've got, some round build chambers now, for example, because guess what? 80% of parts made on large platforms, large area platforms are in roundish in nature.
Yeah. No, I think you're totally right, and yeah, I think if the industry goes towards adopting new technologies for application reasons, not going from 4 lasers to 8 lasers to double productivity, but stay with 4 lasers with beam shaping to
Mhm.
double productivity, certainly the right approach, and you get improved material properties for free. That's not a bad sales statement. Now, new technologies always come with challenges, right? Nothing is perfect. What are some of the hurdles that come with beam shaping, or that you are facing when introducing beam shaping to additive, taking it from a established industry like welding and laser cutting that's been around for a very long time, and now moving into additive?
Yeah.
Which walls are you into?
Yeah. So, it's interesting technically as far as, you know, the laser and the laser architecture goes and what is possible for us. There's, our limits are so further ahead than where the industry is currently. And so that's a little bit of a challenge because we can have the most amazing roadmap around laser technology, but if there's no industry that's really willing and ready to adopt, then there's no point in pursuing that or applying our resources into that. And so that's one thing we need to be conscious of. Our typical process, though, you know, is to work directly with the OEMs. That's really the most important part of market access for us, because it's the OEMs that ultimately will be integrating this laser. And you know, speak of challenges. So you know, one of the challenges is just ensuring that the frame, the build chamber, the optics are all going to be suitable for the levels of power that you want to put through using one of our lasers, the AFX laser. And we believe that job is best done by the integrator. Um, and so we work with OEMs, but then I also think a really important part of our work and our communication is to reach out to the end users because, you know, for example, EOS could say we have this amazing printer and it has this incredible laser in it. But if your customers aren't up to speed with what beam shaping is, what it can deliver, they might not be so convinced. And so I wouldn't say it's a challenge necessarily, but it's just incumbent upon us as a company to do a lot of that end user communication around what can be made possible with beam shaping. And we do that. We do that a lot throughout the year, but we also, you know, we've just had Formnext recently. We've hosted a seminar series, right, which is all around applications in beam shaping. So it's just trying to make sense of what beam shaping can deliver, AFX can deliver. And then as far as any other challenges, we've not even mentioned one software. And, you know, when we talk about 64 lasers, I mean, ultimately you need a brain that's going to drive that, right? And I think that is a larger challenge for the industry to have, you know, we can have the fastest printers in the world, but if we don't have the software that is capable of driving that level of speed, then we will never get there. You know, these things are software operated. We need really fast and really sophisticated software. And on the integration side, that can sometimes be, I mean, not necessarily a challenge, but it's the additional work that is required to ensure you've got those right setting, the settings right in the software and ensure that you can get the full functionality out of the laser.
Okay. Interesting. I mean, do you also, speaking of software, right, and complexity, you know, adding another layer of complexity to the engineers out there that are working on process development, that potentially are customizing processes for certain applications. How much of that customization and process development do you see software driven versus expert and experience driven?
Uh, yeah, I think the way that it goes mostly these things is that you initially have this sort of expert driven knowledge, right? And then
Mm.
that translates or that's kind of codified with software, so that it becomes much more accessible. Um, and yeah, I mean, look, with our customers, the OEMs that we work with, they all have engineers and scientists that are very experienced in process development, and developing those parameter sets that are suitable. I think one of the things, I guess maybe you mentioned complexity, right? Is you give a process engineer, you know, okay, not only can we increase the power, but we can increase the size of the spot size, and we can, and by the way, it's a totally, it's not totally different melt pool, but it's a different, you want to characterize that melt pool in a different way. And so it sort of starts to throw open a whole lot of possibilities. And as I mentioned, that process window gets massively expanded when you go into a beam shaping mode.
Mhm.
And being able to sort through and make sense of all of that is I think it can be a challenge. At a very basic level, you can think about it like we talked about the painting analogy. You can just think, I'm just going to use one mode for productivity and one mode for detail, and that's it. But at a much more complex, more sophisticated level, we can think about this both in terms of geometry dependencies, but also material dependencies, like I was talking about before.
Yeah.
And then also optimizing for quality as well. So there's a lot of things. It's multifactorial. I don't deny that. The good news is you can get started really easily, and then you can always refine from there.
Yeah, I mean, you're just opening up the possibilities and an
Yeah,
application space in the end. And yeah, of course, every new technology starts with experts and early adopters, and then in this case, hopefully, also enables additive to push further into the majority of users and beyond.
yeah.
Um, I want to talk about what's next for NI, but just a small question before we go there. You mentioned aerospace, you mentioned defense. Any challenges you foresee when it comes to certification and standards for additive to adopt beam shaping, or do you think that transition is actually not as challenging as it sounds?
Sure. I mean, as you know, Fabian, certifications are just going to vary. Even within A&D, they vary a lot between A versus D. They vary a lot between is it a program, is it a prototype, and so on. And so uh, most most processes are sort of more, I think, outcome based, right? So in that sense, you're still building a part. And you're building it using known technology, a laser technology and powder that you're familiar with. And so that's kind of less problematic. I think one of the areas though that I would like for us to focus on, and that we have been working on, but I would like us to do this in a more formalized fashion, is to start developing some best practice around beam shaping. Right. So, for example, what is the best way for you to characterize the beam? So you just want to try and look at that beam and characterize it, measure it, and understand what it looks like, and you want to be able to describe it, and do that according to a certain standard that you've prescribed. And so really, I think us as the vendor, it's our responsibility to provide the guidance for that, um, because we can't expect to just create cool laser technology and then just seed it out there into the ecosystem and expect everyone to work it out. Um, and so we need to, like I said, formalize that. We've already done it. It just needs to be formalized. And then the other thing is that, and increasingly this will happen. It's already starting to happen. We had, a wonderful user group forum with AMCM. But that user group, right, is increasingly we have people who have our technology in machine out there around the world, and they're finding different ways of using beam shaping. And that's one thing I'd like us to do a lot more of is reaching out into that end user community, but also really cultivating that community of practice around beam shaping. I know that doesn't necessarily translate directly to standards and certification, but I do think it's a really important part of understanding the ways in which users are using beam shaping to know then how to create some protocol around beam shaping.
Totally. And like always, also then in the end comes down to education, sharing experiences and successes, so that complementary industry partners can also benefit from it.
Definitely. Yeah.
Um,
The whole ecosystem benefits. And I think that's one
yeah,
thing as in the industry, we do really well. We integrate really nicely across the ecosystem of additives.
very true. We could talk more about it, but that's a different story. Okay, now let's talk a bit about the future, because you guys also have some very interesting innovations on the horizon, innovations announced, new programs hitting the market. What should people be excited for when it comes to nLIGHT, beam shaping, and laser technologies?
Yeah. So, and the latest thing that's just happened for us is we were able to launch our latest product, which is a 2 kilowatt AFX. And so, if you think about the significance of that, is in all of our 3D printers, we started with some pretty basic fiber laser technology, right down to 200 watt, 400 watt. 400 watt is still fairly common, across the industry today. And then as an industry got to 1 kilowatt, but really couldn't move beyond 1 kilowatt because of these instabilities created with applying so much power to the powder bed. Now think about that, the fact that we can now, using beam shaping, invite so much more power into our spot size in our average spot size, right? And so we can double that amount of power. There's actually, we could go further than 2 kilowatt if we wanted to. As I was talking about before, I don't, I
Yeah.
think, I don't think that we kind of do need to at this point, only because, um, I'm waiting for the rest of the industry to catch up. There are other things that also need to play nicely with more than 2 kilowatts of power, but 2 kilowatts is really exciting. We've got this product. It's fully through commercial validation with with a commercial partner. Um, and the results that they're showing have been like completely unbelievable in terms of productivity. And that is very, very exciting. So the kinds of applications, it really gets into the heart of what can be opened up when you start to really, really increase the productivity of your machine. You can start to really explode out lots of different applications that were previously locked out to additives that now are available and accessible. So 2 kilowatts, very, very exciting for us. We
Oh,
previously have
yeah.
launched 1500. And now the next step is 2 kilowatt. And then beyond that, one of the things that we're thinking about a lot, and have a lot of products underway, not in additive but elsewhere, which is really around our lasers don't need to just output power. They can be much more intelligent than that. There is a lot of functionality and sophisticated technology that sits inside of a laser, and we can really utilize that for our purposes when it comes to additives. Can't say too much right now, but think of it that your laser is going to get a whole lot smarter and be able to do the things in additives, other functions in additive that you need it to do. Teaser, but
That sounds
hopefully it sounds exciting.
very exciting. Nice tease for the future. Let me actually double click on one thing, because we didn't cover it. I just realized, and I'm curious. So, standard Gaussian laser spot size is what, 80 microns on average, leading to a melt pool of 120 microns, I think, on average. Now, moving to a current standard product of a ring laser, how how much larger does the beam and the melt pool get in the maximum?
Mhm.
And then moving to 2 kilowatts, I'm guessing we can expand that even further, which also has implications on productivity. Can you share some numbers if you
Yeah,
have them?
yeah, for sure. Um, so typically, yeah, like you said, with 80 microns, and for a Gaussian. And for a ring beam shape, your typical number is usually around 230 microns, right? So we can more than double our spot size, and that leads to the equivalent size of increase in melt pool. And that's really the heart of, well, there's two reasons that you can add to the productivity. Hatch spacing can increase, but then you also, due to the nature of the melt pool, can increase your layer thickness as well. So it's like a double productivity sod. And then you're right with 2 kilowatt, you increase that spot size even further, and the melt pool size even further. And then I'll also add to the zoom functionality, which is starting to be increasingly adopted. Can also be applied to a ring, which can increase it even more if you want to. But you can really push the size of your melt pool.
Interesting. Okay, that helps. And on a layer thickness, if I currently run a 80 micron process, how much further can I push it?
So you can, So we've got studies that have shown that you can double your layer thickness. Layer thickness is one of those funny things. It's completely like there are a whole lot of other factors that go into layer thickness and how you would set layer thickness, but it's certainly possible. It's a little counterintuitive, honestly. If you look at the shape of a Gaussian melt pool, it's like this sort of, I don't know, you wouldn't call it quite semicircular, but that inverted bell, right, shape. Whereas a ring beam produces a very sort of pancake-like profile. And so you'd sort of look at that on the surface and go, hang on, the Gaussian, that inverted bell goes a lot deeper than what an inverted a pancake does.
Yeah.
But the fact that with that inverted bell, you need to have a lot more crossover space, right, between those two inverted bells. So your effective depth is actually a lot smaller than your melt pool depth. Okay. So, whereas when you've got this flat melt pool, your effective depth is roughly equivalent to the total depth of your melt pool. So you're utilizing that full melting space for a layer thickness.
And a more cohesive melting, less boiling, as you mentioned
Yeah,
before.
exactly.
Because
Yeah.
reduces the risk of defects going super deep. Okay,
Yeah.
thanks for that little sidetrack. All right, before we end, you've been in additive since 2011, I think you said,
Mm.
right?
Yeah.
So in additive years,
If
which
we
is probably
count
like
cold spray, as additive, then yes.
yeah, yeah. So for quite some time, and you've seen various markets and industries and technologies come and go. How do you see the additive manufacturing industry in general developing over the next 5 to 10 years? And also, what role does beam shaping play there?
Well, hopefully it plays a very large role. Um, I look, conversations with our customers are, along the lines of, we believe this will become the new standard. Which is obviously music to my ears. Like I said, I joined nLIGHT because I really felt like there was an enormous opportunity here that was not being realized, and that this change needed to be affected. So yeah, increasingly, I really hope we see beam shaping and frankly, if we don't, I'm not doing my job. I need to go back to um, but larger, broader industry topics. I'm really excited about large format machine. And I think that what we can achieve with those, and what increasingly we can achieve with those will be very, very exciting. I think additive's been through a tough time as an industry in the last couple of years. It's been rough. There's been a lot of volatility in this market. Even as a vendor to the additive industry, we see that volatility. And that has been challenging. It's symptomatic of this very nascent industry. And so, I definitely hoping to see a lot more maturity coming into the industry. But I also think misery loves company, and everyone tends to focus on the bad news stories and less on the good news stories. And there's so many good news stories. And I think your podcast also does a great job of highlighting those. And so, like I said, as far as broader industry goes, I mean, more, we've already talked about it, large machines, more lasers. It's certainly the way of the future. To think that, the first LPBF machine I bought was a single laser 400 watt, system, to now we're talking about putting in, tens of watts into a powder bed and creating huge parts. I mean, we were making such little parts in the past. And so it's been a wonderful journey for me to be part of this industry over that period of time. And I think that people come and go out of this industry, and that's totally fine. But when you can stay in an area of expertise, that really comes back tenfold, right? Because your experience just keeps building in an industry, and as long as you're keeping that drive for learning, front of mind. I mean, you have to, quite frankly, if you want to stay in additive, because stuff's always changing. There's always new things to learn.
Yep.
Yeah. So let's see what the next couple of years brings, Fabian. And, hey, we hope to do more work with the US as well. I think we've got some really exciting stuff on the boil.
100%. Yeah. And, like you said, if you tell people that you are an expert in additive and you know everything, you're most likely lying. Because it's impossible, because it changes daily, and you need to keep an open mind, and you need to be flexible, and you need to be able to adopt new technologies like nLIGHT for applications that benefit from it. And we didn't even start at 400 watts. We started at 70 watts carbon dioxide lasers.
I was going to say CO2 lasers. I hadn't even gone there.
Mixing bronze with nickel based alloys to melt them, and now we're at 2 kilowatts and more for the future. So I'm excited. I think every industry goes through ups and downs, and it's also healthy to kind of refocus and reset expectations of a certain technology. And I think we're hopefully on the upwind again, and we see lots of cool applications and companies adopting additive for serial production. So unlike you, I am excited for the next 5 to 10 years, and I think we'll see some major changes and adoptions in the industry.
Yeah, well, if the last 5 years is anything to go by, right? And then the 5 years before that, the rate of change is just so phenomenal. You almost get kind of whiplash just thinking about it. But that's what I always think. If the last 5 years was this time to this time, 2019, what was I doing back then versus the next 5 years? I can't wait, and I love being part of this industry and seeing everything that happens, and like I said, continuing to learn is the opportunity that affords us all.
100%. And thank you, Alex, for giving us the opportunity today to learn more about laser technology in general, and the innovations that are coming out of nLIGHT, the implications of beam shaping on additive manufacturing, on industries, on productivity gains and material properties, which in the end will benefit all of us. So thanks for being on the Additive Snack podcast, and thanks for sharing your insights and expertise with us.
Thanks so much, Fabi.
And thank you out there for joining in to the Additive Snack podcast today. I hope you found this conversation enlightening. Oh, that was a good one. I sure learned a lot today, and will take this conversation with me into future conversations. Share it with a friend, share it with a coworker, and also shoot us a message if you have questions about this episode. Alex and I would be happy to answer any of those, and I will see you next time.